Welcome to The Pulse, brought to you by MDT TV. Eliminating the need for surgeons to feel around for tumors while performing surgery, a team of researchers from Canadian Surgical Technologies and Advanced Robotics and Western University have developed a sensor that's attached to a robotic arm compatible with the Da Vinci surgical system. Through an ultrasound transducer that's on one side of the device and a tactile sensor that's on the other, the robotic arm enables a user to sense a tumor. The technology won the Best Innovation Prize at the Surgical Robot Challenge held during the 2015 Hamlin Symposium on Medical Robotics in London. The dual sensor approach provides for a minimally invasive method to detect a tumor, with each type of sensor technology allowing for a different approach to detection without the need for two distinct devices to be used.
Believed to be the first invention of its kind, researchers from Loughborough University have invented a device that converts paralysis victims' breathing into words.
Hello, my name is David.
The augmentive and alternate communication system analyzes breathing patterns and translates breath signals into language with a combination of pattern recognition software and an analog-to-digital converter. The words are then read aloud by a speech synthesizer. Designed for those with partial or complete loss of voluntary muscle control and who lack purposeful movements, the user can essentially create their own language by varying breathing speed. The device has a 97.5% success rate in learning and recognizing words and phrases, and it gathers information more quickly than other similar inventions. It can be especially useful to make an early diagnosis of locked-in syndrome, allowing even patients on ventilators to communicate effectively.
Unfortunately, once human knee cartilage is damaged, it doesn't regrow or heal. As such, doctors at The Ohio State University Wexner Medical Center have used a lab-grown replacement as part of a clinical trial to investigate a potential alternative to current practices of dealing with damaged cartilage. To create the replacement, a surgeon first obtains a small sample of normal cartilage from a patient's knee through a minimally invasive knee scope. The tissue sample is then treated and grown into a cartilage implant, which is returned to the injury site. The grown implant technology is called NeoCart, which is made by Histogenics, the company sponsoring the clinical trial. Wexner Medical Center is one of approximately 30 trial sites nationwide.
Scientists from Korea University and TU Berlin developed a brain-computer interface that interprets brain signals to control a lower limb exoskeleton. Users are clad in an EEG cap and stare at one of 5 flickering LEDs to move forward, turn left or right, and sit or stand. It works because the LEDs all flicker at different frequencies, and the EEG readout reflects the LED the user is focusing on, which is then decoded and controls the exoskeleton. The system succeeds in separating the EEG signal, typically buried under all of the exoskeleton's electrical noise, and is apparently fairly easy to use. Volunteers only needed a few minutes training to operate the system. The exoskeleton could be a valuable tool to aid ALS or high spinal cord injury patients in regaining mobility. For more medical technology news, go to mdtmag.com or get involved in the discussions at Twitter, Facebook, or LinkedIn via the links below. For Sean Fensky, I'm Sam Brusco, and this has been The Pulse.
Welcome